Okay, so the rest of the lecture we're going to be talking about granitoids. Again, not my area of expertise, more of a Mayfic guy. I've tried to make sure that I know what I'm talking about, but it's largely based on Todd's old lectures for this, which I had to cut down a bit just for time. So hopefully we'll get through all the important stuff. So, granitoids. Basically, I've left these till last because everything we've done in the course so far is about mantle melting. And in some cases, like the subduction zones or the continental flood basalts and places like Bushveld, we have talked about crustal assimilation. So there is some crustal melting going on. But the driving force has always been mantle melts and what happens to them. So the difference here is that granitoids are mostly formed by melting continental crust. So it's kind of the other end of melting on Earth. And yeah, we'll talk about all about them. So what are granitoids? They're coarse-grained, they're intrusive, and they're broadly felsic rocks. The definition, I think it depends a bit on who you ask. So some people will have a very, very broad definition of granitoids that includes all sorts of these less quartz-rich rocks like syenites and monzonites. And some people even include some of the silica undersaturated rocks, the ones containing nepheline and those other kind of alkaline silica undersaturated minerals. But the definition that Todd was using, and this is the definition I'm going to use, is that granitoids are defined as having 20 to 60% modal quartz. So that basically restricts it to granites, where less than 65% of the feldspar in them is plagioclase, granodiorites, where 65 to 90% of the feldspar is plagioclase, and tonalites, where more than 90% of the feldspar is plagioclase. The rest of the feldspar, in all these cases, is going to be alkali feldspar. Yeah?
What's modal quartz compared to regular?
Yeah, so modal would be like a volume percentage. You can also do these like normative calculations, right, where they convert the geochemical data into some sort of ideal mineralogical composition. And that's what people often use for plotting on this diagram. But I think for our purposes, if we look at a rock and it's got two feldspars, so plagioclase, alkali feldspar, and between 20 and 60% quartz, we can call it granitoid. So yeah, this is actually it's a bigger range in compositions than it sounds like. And of course here we're just looking at the kind of the silica rich minerals, the feldspars and quartz. There are other minerals in them that we'll talk about later. Granitoids tend to form these pretty spectacular plutons, which are kind of dome-shaped, and you can see a couple of famous examples here. Bottom left is Half Dome in Yosemite, and I can't remember, I think it's about 2.5 kilometers tall, so it's quite a big mountain, but the rock face itself there isn't quite that tall, but it's really quite striking. On the right, you've got Sugarloaf Mountain, which is kind of bang in the middle of Rio de Janeiro. And again, you can see this big dome shape. And so these are plutons. The pluton or plutonic can mean any sort of intrusive rock, but it often gets used with granitoids. It'd be a bit weird to call like a layered mafic intrusion a pluton. People don't really do it. So they tend to have this dome shape. And on a larger scale, we see these batholiths, and I've called them composite batholiths here because they're often made up of lots of small plutons. But they can be these huge kind of elongate bodies. They can be up to hundreds of kilometers long. They can be 100 kilometers wide, so like just a giant sausage of granite. You also see granites in small dikes, although it's not quite as much of it. And then also as veins or dikes in migmatites. And we'll talk about all of these a bit more later. This kind of round weathering surface is really characteristic of granites. And in this case, that's because we're basically following the shape of the pluton. And granite tends to be quite hard weathering and tends to stand up above the surrounding rocks. But also on a smaller scale, when you erode granite, you tend to get these like rounded boulders. And it's quite like distinctive look to it. Okay. So there's basically two end-member models for granitoid formation, one of which is not, I don't think it's really seriously used in most granites, but we'll still talk about it. So the first one is that melting crust makes more silicic or more felsic compositions than the stuff that you're melting. So For example, if you melt intermediate felsic igneous rocks or sedimentary rocks, and these are the main components of continental crust, then you'll get a range of granites and granodiorite compositions. If we melt a more mafic composition, then we tend to get these tonalites, so again, granitoid, but most of the feldspar is plagioclase. The other model, and I think this was more popular in the past, is that if you take a mantle-derived magma and you just crystallize it and crystallize it and crystallize it, you get this extreme differentiation, then you will eventually get to silicic or felsic compositions. So in the top right, I've got a picture of a migmatite. This is a very, very high-grade metamorphic rock where the rock itself has begun to melt. The dark patches in the migmatite are the original rock, and the light patches are little kind of veins of granite that have formed by melting that. And in the bottom right, this is just going back to the Skaergaard intrusion, and this was crystallization of an iron-rich basalt. But by the end stages of crystallization, we're starting to get fairly, granitic-ish compositions. Like here we've got, plagioclase, quartz, K feldspar, plus a bunch of other stuff that you don't usually see in granites. But the idea is that we could eventually reach granite compositions if we crystallize far enough. There are examples where this happens. These are these same dikes that I've shown you a bunch of times, but instead of being thin section pictures, these are taken on an electron microprobe. And so basically the brightness is telling you about the average mass of the elements in it. So the bright areas are heavy elements, so stuff like oxides tends to show up quite bright because iron and titanium are fairly atomically heavy compared to stuff like silica. They don't have any silica in there. But basically in these dikes, you can see this really cool crystallization sequence where the very first stages are olivine and chromite, which are crystallizing from something like a pickrite. Then we get a bunch of crustal contamination, and we start crystallizing orthoperoxene, then clinoperoxene, and actually biotite, which is kind of a weird one, apatite. And then the last stages to crystallize are plagioclase, K feldspar, and over here in this other image, you can see there's also quartz. So plagioclase, K feldspar, quartz, the last little bits of melt in this rock are basically a granite. There is a big problem with this though, and that is volume. If we want to make these hundreds of kilometer long batholiths, we're not going to do it by crystallizing basalt, because otherwise we'd end up with these absolutely enormous volumes of mafic and ultramafic cumulates that we just don't see. So even in these kind of large closed system mafic intrusions like Skaergaard, the amount of felsic melt that you're producing at the end of crystallization is very, very small. So the stuff I was talking about where you had quartz and K feldspar crystallizing was just a little tiny bit either side of the sandwich horizon, the last little bits of melt to crystallize in Skaergaard. There's also a compositional problem, and this is a big one in Skaergaard. The last melts after this extreme differentiation, I said we had quartz, K feldspar, and plagioclase, but we also had all this other weird stuff like phaolitic, iron-rich olivine. We have this wollastonite mineral, ferrobustamite, which is bizarre, and you don't see those in granite. So it's a little hard to make granite from extreme differentiation of mafic magmas, and it's basically impossible to make enough granite to explain what we see. So crustal melting is kind of the model that everyone accepts now, I think, for the vast majority of granites. We don't have volume problems because we can melt as much crust as we want, obviously it's limited by the amount of heat you have available, but we can melt enough crust to explain these big batholiths. And we'll talk about why the crust melts in a bit. We can also see, when we see rocks like these migmatites, this is basically like a frozen in time snapshot of the granite melting process, right? We started with some sort of igneous rock in this case, and we began to melt it, and we have granite, and the granite's not been fully extracted. So we're literally seeing the melt and the residual rock, which is called a restite, in contact together. And there's also a pretty good match between the compositions that people get from melting experiments. So if you take a crustal rock and just heat it up and melt it, and you can measure the composition of the melt that's formed in your experiment, those are pretty close to granite compositions. So we have good reason to believe that most granites come about from crustal melting. All right, so the main points from that granitoids are coarse-grained intrusive rocks, they're mainly quartz, plagioclase, and alkali feldspar. And we're going to be using this definition where it's 20 to 60% quartz. They often form large plutons or even larger batholiths that form composites of many plutons. And they're almost always produced by melting existing crust. If it's felsic or intermediate or sedimentary rocks, we'll get some sort of granite, granodiorite. And if we're melting mafic crust, then we'll usually get a tonalite. Any questions about that? I'm just going to try and fix this because the start bar was appearing for some reason. Okay. So, this is the last bunch of minerals you have to learn. And hopefully some of this is a refresher from last year's courses, but in the exercise this week, we're going to spend a bunch of time looking at different granites. So I wanted to give you a heads up and a summary of the minerals. So I think compared to a lot of the rocks we've looked at, the variety of minerals you can get in granitoids is actually quite large. So there's a lot going on. Some of these we've already covered though, which makes it a bit easier. And some of them are restricted to certain granite types, and they actually end up being kind of characteristic or diagnostic of a certain granite. So obviously we talked about quartz, plagioclase, and alkali feldspar being the kind of defining features. We'll also commonly see amphiboles, and one of them we've already looked at before, hornblende. We saw it in arc magmas, and here's the picture of hornblende from probably some sort of andesite or dacite. We also see biotite, but it's a little important to note that sometimes the colors of amphiboles and biotite are going to be different to what you're used to from the arc magmas. There's also muscovite, which is white mica. And then there's a whole bunch of minerals that are either rare or restricted to certain granite types, or they're accessory minerals, but we'll cover a couple of the key ones. But these include titanite, magnetite, which you've come across before. That's just going to be an opaque oxide mineral. Garnet. I haven't covered garnet in the lectures because if I think there's one thing you guys know how to identify, it's garnet. So we'll leave that one out. Cordierite. It's not super common in granites, but it is important for one of the samples that we look at in the practical. And this is the Cerro del Oyatzo volcano. This is the garnet volcano locality where everyone was looking for nice garnets. Ilmenite, that's another opaque phase. There's these weird alkali-rich pyroxenes, and then a couple of accessory minerals here, apatite and zircon. All right. So starting with quartz, it is low relief, it is colorless, it's usually anhedral, it basically fits in where it can around the other minerals. It doesn't really have a visible cleavage, but you do see these kind of cracks that can look a little bit like the curving cracks in olivine, right? They don't have a consistent parallel orientation. It's low first order interference colors, so it can be gray or white, and occasionally it dips into that pale yellow, but not like you'd see in, say, like a clinopyroxene or something. It'll just be like a grayish washed out yellow. When we look at it under plain polarized light, it tends to look quite clean compared to feldspars. So this one is an alkali feldspar orthoclase, and this is plagioclase over here. And you can see that the quartz, it just doesn't have as much going on. You can't see any fractures in it, you can't see as many kind of like alteration patches, that kind of thing. And then the big thing that I think a lot of you rely on is this undulose extinction. Now, it is diagnostic in quartz, so if you see undulose extinction, then it is probably quartz. The problem is it's not necessary. So this is a picture from a granite, and you can see there's absolutely no undulose extinction in this quartz. So if you see it, it's quartz. If you don't see it, it doesn't mean it's not quartz. There are also other minerals that show undulose extinction, but in general, if it's going to be one of these clear, colorless, low interference colors and it's got undulose extinction, it's probably quartz. All right, alkali feldspar. We've already talked about plagioclase, so I'm not going to talk about it again in this one. Alkali feldspars can look quite different in thin section depending on the exact composition and the temperature at which they formed. But there are some common features. So it's always low relief. It does have two good cleavages at just about 90 degrees, but they can be quite hard to see because the relief is low. It's low first order interference colors. It's only gray and white. You'll never see yellow unless someone's screwed up and cut the thin section too thick. And they're often twinned, but the type of twinning depends on the exact structure. So the structure changes with temperature because of this ordering thing. What that means is at a high temperature, the structure is very disordered. And there are four, I think. There's these different tetrahedral sites here. And basically the aluminium, because there's going to be about 1 aluminium for every 3 silica, the aluminium is kind of spread out evenly. There's an even mix throughout the lattice with silica. Once you get to lower temperatures, the structure becomes more ordered and the aluminium concentrates in these 2 particular sites. And then at very low temperature, it all goes into one site. And because the aluminium ion is a little bit larger than the silica ion, this actually ends up changing the structure.
Question?
Go ahead.
What do you mean by temperature? Is it the temperature at which it's solidified? Or?
Yeah, it's actually a little complicated, and I was going to talk about it here. It's the temperature at which it last equilibrated.
Okay.
And so if you imagine all of these granites and rhyolites have probably been above 700 degrees C at some point. But if you cool them very, very slowly, then it has time for the aluminium and silicon to swap around and rejig and reorder, because basically it's at a high temperature for a long time as it's cooling. So if it cools very, very slowly, it will be in its low temperature form. If it cools quickly, essentially that high temperature form gets frozen in. It doesn't have a chance to reorganize. So sanadine's the high temperature version. It's the totally disordered one. And we only see that in volcanic rocks. So this would be something like rhyolites or trachytes. Trachytes like the highly alkaline version of a rhyolite. And yeah, if it was to cool slowly, we'd get either orthoclase or microcline. Sanadine has these simple Carlsbad twins, just like kind of a straight line down the middle. And it tends to be quite euhedral and kind of blocky, but it's not rectangular like plagioclase. Plagioclase usually has this quite like square shape, whereas alkali feldspar has these sort of, not quite sure how to describe it, almost like a triangular edges to it. So that one can be a little difficult to distinguish from anorthite, calcium-rich plagioclase. But yeah, if it's very, very square, it's more likely to be plagioclase. You can also use context to help you here. So if you have a rhyolitic rock, you're not very likely to have anorthite, but you are quite likely to have sanadine. So this can help you out. Orthoclase is found in plutonic rocks. So this is the kind of thing we'll be seeing in the granites. And as I mentioned before, it's that slow cooling allows it to reorder its structure and go from sanadine to orthoclase. Again, it's got simple twins. This is a great picture actually where you can see the twins in a crystal in hand specimen. This is the lines of where someone's interpreted the edges of the different twins to be. It can be euhedral, like in this case, or it can be anhedral as well. So the shape's not quite as useful as it is for sanadine. It has simple twins, but the big difference from sanadine is it can show this perthitic texture that I'll talk about in a couple of slides. This is basically fine-grained intergrowths of albite, so sodium-rich plagioclase, and potassium-rich alkali feldspar. You never get perthitic texture in sanadine. So if you see this perthitic stuff, and again I'll come back to it, then you can be sure it's orthoclase or microcline. All right, and microcline is the slowest cooling one. It's pretty common in granites. It's often anhedral. You can see here in this picture, these are the microclines here. They're nothing like a typical feldspar shape. They're just kind of like filling in the gaps. And it has this distinctive cross-hatched or tartan twinning. I'm not sure if you have a different name for it that you've been using, but basically you have 2 sets of twins almost exactly 90 degrees, and they're very, very fine twins. It can also show this perthitic texture, and the thing that makes it really easy to distinguish from plagioclase is plagioclase rarely has 2 sets of twins. It can, but when it does, the plagioclase twins are very, very sharp, and they're very, very parallel, so they have very, very straight boundaries between the twins. These microcline twins, they kind of like pinch in and pinch out. You can see, if I follow this one here, it starts here, and then it kind of pinches out by about here. So we have these changes in the twin thickness and this very fine cross-hatching that you just don't see in plagioclase. So that's kind of diagnostic of microcline. This perthitic texture I've been talking about, it forms from the fact that at high temperature you can have a perfect solid solution between albite and orthoclase. So again, when we got sanidine, it's starting at high temperature and it's cooling rapidly before anything can happen. So you never see this. But if you cool it slowly enough, then at some point it hits this solvus, it's called, and below this temperature, anything that hits this curve will split up into two different feldspars. So basically, under this curve, it's more stable to have a potassium-rich feldspar and a sodium-rich feldspar than it is to have one mineral that's mixed together. So basically, depending on the equilibration temperature, these will split and form increasingly sodium-rich and potassium-rich feldspars. So this is something called subsolidus exsolution. It also happens in pyroxenes, but we didn't really have time to cover it. But at some point, the temperature gets too low and you kind of get it frozen in wherever, let's say, I don't know, below 500 degrees maybe, diffusion gets so slow that it's not really changing structure anymore. And you would end up with some sort of feldspar that had maybe 5% albite, 95% albite, and some sort of feldspar that had like 82% orthoclase. The amount that you get depends on the initial composition of the feldspar. So if your alkali feldspar starts off over here, then you're going to get more of this one. It's just the lever rule again. If it starts up over here, you're going to get more albite. And what this looks like is it can almost look like twinning, but it's these very, very fine kind of lenses of the different feldspars intergrown. Pretty much all orthoclase and microcline has this in some way, shape or form. Even if you can't see it, there's this kind of crypto-perthite texture that you can see with other methods you might not be able to see in the microscope. So it's part of the reason that orthoclase tends to look quite like, you know, dusty and crappy in comparison to something like sanidine that can look quite clean. Sanidine's never got this perthite. Okay, so that was alkali feldspars. Muscovite is white mica. It's colorless. It's got low to moderate relief. So you can actually see that here. You can see some of the cleavage planes. The color is the most distinctive thing from biotite, which, you know, it can either be green or yellow or brown, but muscovite's always clear and colorless. It usually forms these kind of thin sheets or flakes that you can see up here. Just like biotite, it's got one perfect cleavage. That means a really, really strong cleavage that's usually visible in the thin sections. It has second order birefringence, so it's actually a lower birefringence than biotite, but that means you get these really, really vivid colors. So it's kind of similar to the olivine colors. It doesn't have quite as high birefringence as olivine, whereas biotite is up to fourth order and you start to get these more like pearly colors going on. And finally, just like biotite, it's got speckled extinction, and that means that when it's in extinction, it's never quite black. It's like someone's poked little holes and you can see a bit of light shining through it. Titanite is this weird calcium titanium silicate. It used to be called sphene, and sometimes you'll still see that name for it. But that comes from the Greek word for wedge, because it's wedge shaped. So I hope that'll help you remember it. Yeah, it's got super, super high relief. Again, it looks like someone's drawn thick outlines around it. It tends to be colorless to yellowy brown in plain polarized light. And the birefringence is so high that when you put the polarizer in, it basically just looks the same. So it's a bit like calcite, where it starts to get those super washed out pearly gray colors. But because it's got a bit of color to begin with, when you actually put the polarizer in, it just looks the same. Basically can't see any birefringence. Cordierite, this is actually a ferromagnesium mineral, but it's very, very rich in aluminium. So it's got almost as much aluminium as silica. It's present in the Cerro del Hoyazo volcano, the Garnet volcano that we visited, and it's that I think is actually the type locality for cordierite, which is kind of funny because cordierite is probably much more common in metamorphic rocks, and there's only a few, granitic volcanic rocks that you see it in. It has low relief, it's colorless. In terms of twinning, it can look quite similar to plagioclase in that sometimes it has these polysynthetic twins. The big difference from plagioclase is that the twins tend to pinch out. So again, plagioclase has those very, very parallel twins. Cordierite, it can make these kind of like lenses or wedges that just kind of end. It's also only got first order greys or whites in terms of birefringence. If you see this type of twinning, which you get in some corderites, it's called sector zoning or cyclical twinning, and it basically looks like someone's taken a pizza and cut slices out of it, and that's quite diagnostic of cordierite. If you don't have this type of twinning, it can be difficult to distinguish from feldspar. There's obviously the fact that the twins pinch out, but there's a couple of other things you can look for. It alters to chlorite because it's a ferromagnesium mineral. So that chlorite is that kind of greenish sheet silicate with the weird interference colors. It tends to have quite a lot of inclusions, and if it has something like zirconin, which are these little grains here, then you'll get these, they call them pleiochroic halos. These are basically radiation damage around the zircon, and you won't tend to see that in plagioclase. All right, now the very last thing is just to make a note about the type of biotite and amphiboles we get in granite. In the subduction zone rocks that we've looked at so far, biotite was almost always brown and yellow pleiochroic, and amphibole was almost always this kind of brown and yellow again. Biotite can be green and yellow, so I don't remember if there's any in this section, but this is probably biotite up here. Amphibole can be all sorts of colors, so we'll also get hornblende just like in the subduction zone rocks, but it can be green in granites as well as brown and yellow. And then some of the alkali-rich amphiboles that we'll talk about later can be everything from this kind of teal green to purple. So the key thing here is to look for the cleavages, and that will be maybe a bit more useful than color. All right. Most important minerals in granitoids are quartz, alkali feldspar, and plagioclase. Alkali feldspars look different because they have different cooling rates, which causes the formation of different structures, which can ends up changing the way they look in a microscope. So we have sanidine in volcanic rocks like rhyolite, and we have orthoclase and microcline in plutonic rocks, and these will both show perthite. Muscovite, white mica, biotite, and amphiboles are also common, but you have to be aware that the biotite and amphiboles might have different colors than what you're used to. Any questions about that one? All right. Okay. Talk a bit about crustal melting. Yeah, so at the very start of this, we were talking about how granite is defined as quartz and two feldspars, so plagioclase and alkali feldspar. So a lot of the early experiments to do with forming granites were performed in this albite orthoclase quartz ternary, and that's basically albite, sodium-rich plagioclase, quartz is just quartz, and potassium feldspar is orthoclase. So when people did melting experiments in this system, they find this thing called the granite minimum. I've put in brackets wet here because these experiments are water saturated. That means they put as much water as they could physically get into the rocks. And it's called the granite minimum because it's the lowest temperature silicate melt that can exist. It's the lowest temperature silicate eutectic in one of these ternary systems. So what that means is either if we take something and do extreme fractional crystallization until we've got nothing left, the last melts will tend to be granitic and they'll be sitting near this eutectic. And also if we have some sort of quartz feldspar rich rock, like potentially a sediment or a felsic igneous rock, then the first melts to form will be at this granite minimum eutectic. All right. So just going back to the phase diagram stuff we talked about before a bit, if we have a melt like A, it's going to start off in the quartz and liquid field. It's going to crystallize quartz. It's going to move away from that corner as we remove quartz. It's going to hit this cotectic, This cotectic intersects somewhere around, it's probably closer to 60% K feldspar, 60% quartz and 40% K feldspar. No, I had it right the first time. 60% K feldspar, 40% quartz. That's just doing the lever rule. This is 60, this is 40. We're closer to K feldspar, so there's more K feldspar crystallizing. And then the melt's going to move down this eutectic until it reaches this minimum point. When it reaches the minimum point, it's going to sit there and crystallize 34% quartz, 26% K feldspar, and 40% albite until all of the liquid is gone. And that's just done using this ternary lever rule, where we measure the distances through the eutectic point to the other side, and we divide this distance by the total to get the percentage in the crystallizing assemblage. So that is that there. All right, the exact composition of melt that we get at the eutectic and the temperature at which that eutectic point sits depends on the pressure and the water content. So as we talked about with the subduction and stuff, water is less soluble at low pressures, it tends to degas, and so the water content depends on pressure. So if we're at zero pressure, we basically can't hold any water in the melt, and so the melt would be a dry granite. As the pressure increases, the melting temperature of a dry granite goes up, but we can also fit more water in the melt. So by about 200 megapascals, we can fit 6.5% water, and I think that's about 2 kilobars, so something like 6 kilometers maybe depth. So we can fit 6% water, and once we're getting into kind of the mid to lower crust, we can actually fit a lot of water into these melts, so 10-11%. Now looking at this, you can see the temperature for dry melting is way, way higher than wet. So if we're at 200 megapascals again, dry melting is about 1,000 degrees. Water saturated melting, which would be where this curve gets intersected, would be about 680 degrees. So it makes a huge, huge difference. So in terms of melting the crust, this is often called anatexis, which is just another way of saying partial melting, but people use it pretty much only for crustal melting. You don't tend to say like mantle anatexis. So crustal melting happens at high metamorphic grades. So I've got two diagrams here because this one doesn't really show the metamorphic facies, but it does show the wet melting curve and the dry melting curve. So this wet melting curve is somewhere around 700 degrees C, and that's up around the upper amphibolite facies. If you wanted to do dry melting of granite, then you have to get up into like high granulite facies around 1,000 degrees C. The main process for melting is dehydration melting, and dehydration melting is where minerals, hydrous minerals, so this would be stuff like micas or amphiboles, they break down with increasing temperature. As they break down, they release water, and then you're able to have wet melting. So you change the solidus temperature because there's water there. That melt, if it then escapes, it tends to take the water with it because water is incompatible. It goes into melts, and so the residues are left drier than they started out after the melting has happened. So as an example of this, Cerro del Hoyazo, the garnet volcano again, it's a great example because we can see chunks of the restite in the lava that was formed. So the protolith to this was probably some sort of graphitic, just means it's got graphite in it, metapelite schist. So this would be like the stuff that we saw when we went to look at the metamorphic rocks. We kind of drove over the top of that ridge and stopped, and we could see there was these mica schists with not much else going on, very, very dark colored metamorphic rock. So the degree of melting that's been estimated for this is that if you took that kind of schist rock to begin with, you have to melt it about 40 to 50% to make this dacite, and the melting temperature is about 850 degrees C, and it's about 20 kilometers depth, so in the mid-crust. The melt that was produced has dacitic glass and then phenocrysts of biotite, plagioclase, pyroxene, amphibole, and cordierite. And the restite, which is the leftover residual stuff from the melting, This appears as xenoliths and xenocrysts, and you can see garnet, sillimanite, cordierite, quartz, biotite, plagioclase, graphite, ilmenite, and spinel. And so here's a picture of the restite. Again, this was brought up in the volcano, and we could see chunks of it in the field. Here's garnet. This kind of like grayish fibrous stuff is sillimanite. The brighter stuff here is plagioclase, and then the dark stuff in between is a mix of biotite and graphite. So yeah, in this volcano, we basically see both bits, and we've seen the protoliths somewhere else, that kind of schist. So I'm not quite sure what the differences are in between these different graphs, but it was in Todd lectures, and I think it's pretty illustrative. So if we increase the temperature of a metasediment, so at the top here we've got a metasediment that's made of garnet, plagioclase, quartz, and muscovite, and a tiny bit of biotite. Basically, as we increase the temperature, we hit a point where muscovite, which is the hydrous mineral, starts to break down, and as muscovite is breaking down, we're producing melt. With increasing temperature, we're releasing more water from breakdown of these hydrous minerals, and we're increasing the degree of melting, so we're getting more of the original rock is now melt, and less of the original rock is this restite, this residue from melting. Same here with what looks like a different composition. We've got garnet, plagioclase, quartz, tiny bit of muscovite, and a bit of biotite. And there's this kind of initial burst of melting with the muscovite, but then the muscovite disappears, and then we have slower melting, and we're gradually getting rid of biotite, and ending up with quite a lot of melt at quite a high temperature here. So yeah, as we go in this direction, we're losing restite. It's getting molten. It's getting added to the melt. We're breaking down hydrous minerals, and we're making the restite drier. We're losing water from it. So the melts are granitic, and they're what we call water undersaturated. So the melts could hold more water, but they aren't. The water that's being released is less than the total amount of water that the granite could hold at those pressures. Go ahead.
What was restite?
Restite is just the residue from melting, the leftovers. Yes, so in terms of where melt is produced and how much melt is produced, the mid to lower crust is rarely saturated in water. So if we look at these different melting reactions here, this is the water saturated solidus, and this is basically the exact same thing that I showed you on this one. This is where it would start to melt if there was as much water as you could physically hold in the melt. But yeah, the mid to lower crust is pretty dry. It's often made of these high grade metamorphic rocks that have already been dehydrated. So melting doesn't always begin at the wet solidus. Usually this is going to start when the lowest temperature hydrous mineral breaks down, and in terms of metasedimentary rocks, often muscovite. So this phase diagram is pressure against temperature, and it's showing this is the wet solidus, and then this one here is a line for this reaction. Muscovite, plagioclase plus quartz goes to K feldspar, some aluminosilicates, this would be something like sillimanite, and a liquid. So this is where it starts to melt. So if we were heating up a rock along a normal geothermal gradient, we get no melting here because there's not enough water. But when muscovite breaks down, that's when we start to get melting. So this kind of first melting is kind of limited because there's just not that much muscovite in a lot of sedimentary protoliths. But when you get to even higher temperatures, biotite breaks down, and this is a different reaction. Biotite plus plagioclase plus aluminosilicate plus quartz goes to K feldspar plus garnet plus liquid. So we've got another melting reaction, and this one's happening from breakdown of biotite. So if we go along this geothermal gradient, 25 degrees C per kilometer, we have no melting here, tiny bit of melting when the muscovite breaks down, then lots more melting when the biotite breaks down. And what that looks like, if we just plot the melt fraction against the temperature, is we get a little blip of muscovite melting, keep heating up, then biotite breaks down, then we get much more melting. And then after that, if there's no hydrous phases left, then the melting slows down a lot until the temperature gets much higher and we get up towards the dry solidus. So metabasalts can also undergo dehydration melting. Here, it's less likely that you have micas, and most of the melting is happening because of amphibole breakdown. So if you think, you guys have done metamorphic rocks before, right? Or is this all? Okay, good. And if you think about the different metamorphic facies, you have the boundary between amphibolite and granulite facies, and it's defined by this breakdown of amphibole. So what's usually happening here is that amphibole, in this case hornblende, is reacting with silica. In this case, it's drawn as quartz. This will happen even if there's no free quartz in the rock. And you'll produce a melt, and you'll produce orthoproxene, clinoproxene, maybe some garnet, and some plagioclase. And now this orthoproxene, clinoproxene, and plagioclase is kind of the defining mineral assemblage of granulite facies. So it's this hydrous melting that makes that change. But in terms of what we're interested in, this is another way of making granitoids. So generally you get these tonalytic compositions, so they're high in calcium, they're high in sodium, and that means you get lots of plagioclase compared to K-feldspar. So yeah, similar thing here. This is the amphibolite facies field. This is the wet melting curve, and you can see about this same place. This is where the amphibole breakdown is, and that's where you'll start to get granitoid production. So with this one, it's the same plot as the ones we did for sedimentary. We have quartz and hornblende, which basically get reacted out of the rock, and at the same time we produce melt. And only once the temperature gets higher, we start to get significant amounts of dry melting of this leftover plagioclase, clinoproxene, orthoproxene assemblage, and that will it will produce more melt, but we need to get to a much higher temperature. All right. So the ternary system, albite orthoclase quartz, is the lowest temperature silicate eutectic. It's called the wet granite minimum. Felsic or intermediate rocks and sediments that are undergoing heating produce granitic melts that are quite close to this granite minimum composition. Mafic rocks melt and form more tonalytic compositions. Most crustal melting is driven by dehydration melting, where hydrous minerals such as muscovite, biotite, and amphibole break down and release water. This lowers the solidus, and then you produce melt. The melting progressively removes water, and it leaves this dry, refractory restite that is then harder to melt because it's had the water removed from it. Any questions about that? Nope. Okay, that was it. So, we can probably have 10 or 15 minutes. Depends whether you want to leave early or have more of a break. Leave early? Okay. So we'll see you back at 3:05.